Good afternoon, everyone. I'm Poorva Tiwari, a computer science student at PES University, India. This research work, Secure Wipeout in BYOD Environment, was carried out as part of my final year project along with two peers, Sanjana U and Skanda CS. Professor Prasad Honavalli and Ms. Aruna S were our supervisors. This is the outline that I'll be going through as the presentation progresses, starting with introduction, objective, proposed work, that is two profile deletion methods, followed by results and discussions, conclusion, and future work. Have you ever wondered what happens to the files you delete on a daily basis? When you first delete a file, the respective file is moved to the trash directory or recycle bin or something similar depending on your operating system. They continue to stay in this directory and occupy the disk space until you empty the trash or delete the files permanently. But is permanently deleted data ever gone from your device? A very common misconception is that deleted files are completely removed from the hard drive and that they're never recoverable. There's a growing concern of data theft and the need to securely delete confidential data, which may include corporate, government, or even personal data. This was one of the key motivations for this research work. We have taken BYOD as a use case for secure deletion. So BYOD, which stands for Bring Your Own Device, is an increasing trend where employees use their personal devices to connect to their organizational networks and access work-related systems. There are several advantages of adopting BYOD. Allowing the employees to bring their own devices to work can create a more open, efficient, and a relaxed environment that benefits both the parties. This has become even more popular amidst the pandemic, as most of the employees around the globe are working from home. Due to performance and deletion latency, erasure of data in most file systems today results in unlinking the file location and marking data blocks as unused. This may suffice the need of a normal user trying to delete unwanted files, but the file content is not actually erased from the data blocks and can be retrieved with the help of various data recovery and forensic tools. In common BYOD programs, the personal device in use is completely wiped out. On the other hand, most of the companies make use of VDI, also known as Virtual Desktop Infrastructure. One common example is mobile device management. With the use of virtual workstations, there is no focus on data saved by the employee on the personal devices. However, employees commonly use text editors to store code snippets or to make notes, notepad stickers, and other such applications of files on their personal devices. One of the business challenges in implementing BYOD is deleting company-specific data when an employee leaves an organization. Erasing the entire drive just to delete company data is not just time-consuming, but may also lead to deletion of personal data. It also harms and reduces the performance of the hard disk. The two main objectives of this research is secure and selective deletion, which are extremely important in this scenario. We have limited our target device to be desktop or laptop. I'll also be mentioning specific file systems and operating systems that we used for this work as we progress. In order to securely delete specific data, we have implemented two per-file deletion mechanisms, overwriting data and encryption-based deletion. We used Stellar Data Recovery tool to verify the conduction of all the experiments carried out. Just to give you context on this, it is a freely available tool which is compatible with most of the common file systems. It helps in the recovery of lost volumes, deleted, and formatted files, and also supports encrypted storage drives. There are various overwriting methods such as complete overwrite, delete block, delete sensitive, and random overwrite. In complete overwrite, the file is completely overwritten with random data or 0 bits. In the delete sensitive method, data is first classified as sensitive or insensitive, and only the sensitive content is overwritten with random values. In the delete block method, the blocks containing the sensitive information are overwritten. Random overwrite involves overwriting random bytes of data in the disk, making it the least secure approach. Among the 4 categories, although the complete overwrite method is computationally expensive, it is the most secure method. Hence, our approach for per file deletion technique uses complete overwrite method. In our implementation, a given file is overwritten with either random data or no P instructions in hexadecimal representation based on the user's need. No P instruction is also known as zero override. The number of times the file should be overwritten can be specified by the user. This was performed on a 1 GB external flash drive in APFS, which is Apple File System used in Mac OS, and exFAT file systems used in Windows and Linux. For this approach, the user needs to provide a file path, number of override passes, and type of override data, either 0 or random. In both the file systems, APFS and exFAT, the contents of 8 different PDF and text files were securely deleted by 0 and random data override. We used 1, 3, 5, and 7 override passes. The PDF files, after being overwritten, were not recoverable in both the file systems. It was not readable by PDF viewers, such as Preview or Adobe Reader. This is due to overwriting the formatted content other than the flat text in the PDF. For the C++ or CPP code files, the content of the files after overwriting could be observed using a text editor. The files recovered using the Stellar Data Recovery tool are shown here. The first screenshot refers to a file overwritten with zeros, whereas the second file was overwritten with random data. The tool was able to list out the deleted files as the metadata of these deleted files were not tampered. Only the data blocks corresponding to the file were overwritten. The recovered files did not contain previously existing confidential data. Moving to our next implementation, encryption-based deletion. In this, we first encrypt the file using 128-bit AES encryption algorithm and then delete the encrypted file. The choice of algorithm is based on optimal security and performance. The encryption key is generated using PBKDF2, which is a password-based key derivation function. A user-given passphrase is concatenated with a random string and is passed as an input to the function which uses SHA-256 internally, along with a cryptographic salt, to repeatedly hash the password with the salt 1,100 times as recommended by NIST. This generates a random key that is truncated to 128 bits. To avoid leakage of the encryption the key is temporarily stored and computed in volatile memory, which gets erased every time the system is restarted. Once the target file is encrypted, the key is overwritten with a randomly generated string in the memory, making it more difficult to steal or recover the key. This process is followed by deletion of the target file. On using the Stellar Data Recovery tool, no data was recovered. Although the files recovered contained encrypted data, which succeeded the purpose of secure deletion. Additionally, we extended per-file deletion methods to directory level deletion based on the given path. All the files and directories in the specified directory were recursively overwritten or encrypted and then deleted in a similar fashion. Moving on to the results section, commonly used secure deletion methods aim to securely erase an entire partition which can be time consuming. With this implementation, we were able to securely wipe out selective files. This is a faster approach when compared to wiping out an entire disk. It was observed that a single overwrite was sufficient to securely delete the file such that no meaningful data was recovered. In modern systems today, the mechanisms such as copy on write and cache technology either delay or prevent overwriting the data blocks with zeros. Therefore, overwriting the content once is sufficient to securely erase data. We also observed that the time taken to overwrite a file increases linearly with multiple number of passes. We had taken a 200 MB file here. Overwriting several times is again accompanied with performance and computation overheads. Next, we compared the time taken by zero overwrite, random data overwrite, and encryption-based deletion for different file sizes, 100 MB, 400 MB, and 700 MB to be precise. The first graph compares time taken by encryption and zero-based deletion, where encryption is faster. In the second graph, we observed that the overwriting files with random data takes much more time than zero-based overwriting. On the other hand, encryption is much faster than both the overwriting data solution. Although encryption is an ideal candidate for a fast erasure process, it has its own drawbacks. To start with, handling of keys is quite cumbersome. There can be more backups to the key. The unpredictable pace of technological development would render many encryption methods unreliable in a few years' time. To conclude, we have presented two approaches to securely delete selective files, namely overwriting solution and encryption-based deletion. In a BYOD environment, if isolation between corporate and personal data is maintained, which means the data is separated by using different partitions, drives, disks, etc., secure deletion of the partition or the drive can be achieved by overwriting the entire disk. However, to securely delete only company-specific data, per-file deletion is possible for a range of file systems as observed for APFS and exFAT. Simple per-file deletion methods are not only faster than secure deletion of an entire disk, they also help reduce performance and computation overheads. In future, we aim to implement the following. Firstly, in our implementation, we have considered deletion of data blocks corresponding to the file content. We would like to extend this to metadata deletion as well for increased security. Secondly, our work focuses on secure deletion of the latest updated version of the file. In case of NAND flash drives, a series of updates are made at a new location for every file update. Similarly, for a hard drive with in-place update, the latest version of the file might occupy less disk space compared to a previous modified version of the file. In order to track and securely delete these data block locations, future work concerns a mechanism to track the files to be securely erased from the moment of file creation and identify file system events such as updation and deletion. Thank you for your time.